Hello, everybody. We are in Berlin, taking advantage of doing a QRI meetup here, also presented at SciDAO. I'm also going to be presenting in a couple of days, actually tomorrow, for an event by Foresight and on AI Hope. But yeah, not taking advantage of being here. Libor came over. It's been fantastic hanging out with him and Beta and other QRI people. And yeah, we decided to take advantage of our physical presence to do a lot of work, but also produce some fascinating content. For context, we've been talking a lot about the difference between functionalism and implementationalism. And I think it's it's very good to have Libor here because he's explored a lot the space and had a lot of functionalist intuitions. And I think in our latest conversations, finally he's starting to grok some of the implementationalist perspective of the Qualia Research Institute.
Yes.
And so we're gonna go through philosophical background assumptions and ideas and solutions to key philosophical problems that QRI is proposing. So let's go.
I want to make this interview as from first principles as possible and really dig into QRI assumptions from the very top or from the very fundamental level, however you frame it. They are both like this, and find really the deep players from which the deep generators from which QRI content is basically emergent on top of. So, and that seems to be that lots of people cannot seem to grok much of QRI sometimes, since they just operate in different assumptions, which just is then not as compatible with their worldview. And we can try to find more of a bridge in this conversation, I think. Or at least explore the landscape and stuff like this. So
as a note, it's very common for philosophical discussions to be derailed by implicit differences in background assumptions. So making them explicit and working through them and substantiating them is always a really great idea to actually have meaningful conversations here.
So we'll go over the philosophical assumptions, we'll go over ontology, we'll go over that the QRI is using. We'll go over what maths that QRI loves to work with, what empirical evidence focuses the most on from various fields like physics, neuroscience, and so on, and how on top of that the QRI Gameplex is basically built and QRI research in general. So that should work. Also, I try to come up with different alternative positions to different parts. So let's see how that will work out.
Fantastic.
Yeah. So, okay, first part is motivation. So what are at least on the vibe level or on the also philosophical level, what are the biggest generators? And the goal of QRI seems to be, or one of the biggest part of it, seems to be reverse engineering consciousness as much as possible. So on the neurophenomenological level, you could say, which is fusion of neuroscience and phenomenology, where phenomenology is the study of direct experience, basically. So trying to connect these two together and helping all sentient beings with that knowledge. So engineering paradise. So we're figuring out how suffering works, how bliss works, and then using that to engineer better world for everyone, basically.
Exactly.
More motivation, more well-being and stuff like this.
Yes, figuring out consciousness to help sentient beings.
Yes.
It's very simple at the end of the day.
Yes. So QRI wants the model to be predictive. So it doesn't want models which just don't give useful predictions, I would say, for engineering, and wants to maximize valence, both individual and collectively, I would say, which is this help all sentient beings part. And big part of it is also a lot of exploring, right? So exploring the state space of consciousness, basically, as much as possible, map it out.
Part of the bet here is that just as in physics, it's extremely difficult to come up with fundamental equations for physics if all you have access to is room temperature phenomena. Like, for example, you would never guess that, hey, water turns into gas, right? Like vapor and then plasma, unless you expose it to really high temperatures or, superfluid helium and all of the exotic properties. The same with consciousness. I mean, there's a lot of things that happen in consciousness in exotic conditions, like meditation, psychedelics, dissociatives, strange psychological effects, and so on, that we think are like actually meaningful and significant for understanding the equations of consciousness and its function, why evolution recruited it. And so, if psychology is just, focused on like everyday modes of consciousness, is just like physics trying to figure out everything through just room temperature. It's not gonna work.
Yeah. That's good intuition. Yeah, and also one of the generators is connecting. So connect people together, connect empirical evidence together, I would say.
Yeah, I mean, are you talking about, like the oneness and so on?
Yeah, this is
cover that? Or not? Okay.
This is the meta one.
So I mean, I guess this is kind of grounding it in values that are useful. That we have like 3 generators that we really care about. I mean, one is like exploration, understanding the state space of consciousness and figuring out its properties. The second one is like happiness and bliss and connection and love. Like that's a really key value and like region of the state space of consciousness that we think is essential. And finally, like sustainability and health. Like how. What kind of patterns are actually compatible with a human organism, that also really matters. So that we don't end up in a situation where this maximizes valence, but also cuts your lifespan by 20 years or something like that.
Yes, sounds great. Okay, so let's move on to the fundamental assumptions in philosophy.
Yeah.
So first, what even is consciousness? How does QRI define it? I see there seems to be infinite amount of definitions in different schools of thought, basically. So QRI definition seems to be very simple, and it's just that the system is having qualia.
Yeah.
And what is qualia? It also has multiple definitions. The system having experience.
Yeah.
I think that's the simplest definition you can find.
Yeah, like the study of experiences, taking experiences seriously, like you right there, you're having an experience right now. And okay, what is its nature? Qualia is the raw basic properties of experience, like the blueness of blue. That aspect of experience that is very hard to describe, but is perhaps the most important because it's actually determining the nature of your experience.
Yeah, and also since we say experience is like the fundamental core that we want to reverse engineer, there are people like illusionists who hold the position actual experience doesn't exist. So that's one thing that if you postulate, then sorry, it's probably hard to merge it with what QRI is doing.
Yeah, essentially.
Yeah. So that's Qualia Realism, basically, the opposite of illusionism. And then another assumption is Qualia Formalism. So Qualia itself can be formalized, and what QRI is formalizing it with is subset of analytical philosophy, we could say, the mathematics essentially, and as ideally as empirical as possible, so using physics.
Yeah, I mean, just to state the definition very clearly, Qualia Formalism first defined in Principia Qualia by Mike Johnson. It's a very powerful generator. I mean, what it says is that for any given physical system that is conscious, there will correspond a mathematical object that is isomorphic to that system, such that the mathematical features of that object correspond and map onto the phenomenology of the experience that the system is generating. So it really is kind of this square, like system, mathematical object. From the mathematical objects you got the features, and then from the features you go to the phenomenology. And so this is how you connect a physical system to what kind of experience it's generating, with a bet that there is a mathematical object underlying all of our experiences. And by reading it, you could read what the experience is like.
Yeah, and some people would say that actually you cannot formalize. Qualia can be only approximated by math. Therefore, the math doesn't ontologically exist.
Yeah, I mean, in some sense, it's kind of a... Qualia is the fundamental makeup of reality, is one kind of ontology that we play with or we take very seriously. Mathematics, it's a very interesting thing, but in some sense, mathematics only exists in the mind, ultimately. And there's a lot of subtleties here. But, even when you think of a point, we would argue that you're not really instantiating a Platonic point. What you're doing is within your field of experience, you're focusing on a region of it, and kind of there's this waves of attention that concentrate on it. And so, even thinking of a point actually requires something much more complex. And so when you're doing mathematics, you're not really interacting with Platonic objects. Rather, you're shaping your experience in such a way that the interactions are isomorphic with the objects that you're exploring. Just a subtlety. But yeah, mathematics here wouldn't be exactly fundamental. Qualia is fundamental, but qualia can be modeled mathematically.
Yeah. And there are also schools of thought where you cannot approximate qualia at all, which hard to actually fit inside the QRI paradigm, which has the assumption that you can actually approximate it.
Yes.
So at least approximate.
Yeah.
Or maybe fully formalize. Well, we still don't know. Same with physics. Yeah. So another fundamental assumption is oneness, right? So all systems with qualia are matter, basically. They are valued. So yeah. If you wanna...
Yeah, so oneness, we think that's like very important because, you could care about consciousness, but you could, be very tribal, for example. You could say like, well, yes, but the only consciousness that matters is my consciousness or the consciousness of my tribe or my country or something like that. We take the position that every experience matters. Like that this sense of like, oh no, only my family matters or something like that is like, that's an evolutionarily inherited illusion, a way in which we, assign value to states of the world, but that is the selfish gene at work. If you care about like the deep truth of ethics and reality, every experience in some sense is equally important. Weighted by are they suffering or are they happy? Yeah. Ethically speaking, yes.
Which lots of effective altruists love this position.
Yeah.
So that's one alignment there. Yeah. And another assumption is math. So we already described it that we can formalize qualia using math. So assumption is math is great. Let's use it.
Yeah, math is a key generator. You will find, for example, some like religions or mystical views that says like, yeah, consciousness matters, but like math, I'm not sure about that. But no, we care about quantities and qualities and amounts, right? Like it's not the same like suffering 1 year versus suffering 1,000,000 years. Differences in quantity and quality matter, right? Like, so that's, hey, math is important.
Yes. And also valence realism. So maybe you can define valence?
Yeah, valence is a very general term that roughly says how good or bad an experience feels. It's more general than, let's say, like just happiness, because happiness is kind of a psychological state. And more general even than pleasure usually is associated with kind of like, like good states of the body or your representation of the body, like warmth or something like that. Positive valence encompasses all of that, like joy and tranquility, even equanimity and sense of ease. All of those have positive valence. And likewise, negative valence is not only about pain, it's also like, psychological discomfort or, like rattling sensations, like anything that kind of is disturbing and unstable tends to be kind of like negative valence. And so like valence realism is to say that like, no, this is not a cultural thing. It's not anthropomorphizing or something like that. It's not the case that like, oh, who knows if a pig can suffer or something. No, all experiences have some valence. A lot of them have neutral valence, like maybe they don't care whether they exist or not. But yeah, no, at least evolved experiences tend to have a lot of valence. Most people like, and this is culture neutral. This is not just a Western perspective on the world. Valence realism is going to say like, this is universal.
Yes. And also the assumption is that we can find a mathematical formalism for valence, basically.
Yeah, so that would be valence structuralism. So valence realism is more broad. You could be a valence realist and say, yes, experiences feel good or bad, there's something true about that, but that's a metaphysical, impossible to model feature. Some people, for example, have this view that valence is related to how close you are to God or something like that. And then they might say like, yeah, that's non-mathematical, non-computational, it's transcendent. Whereas we would say like, no, actually, if you feel really great because you feel very close to God, that is because the structure of your experience while you're having that sense of connection has mathematical features or structural features that correspond to positive valence.
Yeah, maybe the simplest example that has been experimentally verified already lots of times, is that higher levels of the neurotransmitter dopamine seems to correlate with higher valence, essentially.
Yes.
So there seems to be at least some link, at least some way to quantify it. It's at least, this is like one possible starting point you can take to take this assumption seriously, basically.
Exactly.
And then we can expand on it infinitely, find all the correlates and so on. So now philosophical assumptions that are more on the metaphysical level, I would maybe say, on the ontological level, that QRI works with non-materialist, physicalist idealism, and from that follows that it's panpsychist, that it's non-dual, and that it's monist. So if you want, you can elaborate on that.
Yeah, so it's a mouthful, right? Like non-materialist, physicalist, idealism. So first of all, physicalism means that the laws of physics describes the universe. We don't introduce like new physics, we're not, there's a lot of people who like try to solve consciousness by saying like, oh, the physics is incomplete. And there's like maybe this equation or this perspective that like, captures what consciousness is within physics. We tend to say at QRI, like, no, physicists really know what they're doing. With a standard model, you can predict, up to, I don't know, like 17 digits of precision, how particles will interact in a, particle accelerator. It's like, there's clearly some ground truth to this. It's not made up. It's not complete, but, that's kind of like the job of physicists. It's not something that we are likely to ultimately really help with, except in some very speculative scenarios that, I'm not going to go into. But like physicalism is the behavior of the universe is described by the laws of physics. The thing, though, is that physicalism is silent about what it is that it is describing. So then you need kind of like an additional component, which is like, okay, but what is it? What is the universe? A materialist perspective is, the universe is made of insentient, dull, kind of like non-conscious matter. It's this additional assumption on top of physicalism. And there's like a lot of problems with it because it's like, okay, but at what level does consciousness emerge and how does that work? And you have a lot of kind of like philosophical problems. We solve that by saying like, no, we believe in idealism, which is that the fundamental nature of reality, the fire in the equations, as it were, is qualia, is consciousness. Another way of saying it is like, consciousness, your experience, reveals the intrinsic nature of the physical.
And so there's no duality. You could say the physics itself is the consciousness. Mathematically, there's an isomorphism there, basically.
Exactly.
And it's monist, so they are not divided, which is the non-duality part. And in panpsychist, since all of physics is physics of qualia, basically.
Exactly.
So that's the philosophical assumptions. Now, another assumption is no solipsism. So there are different experiences that actually ontologically exist. There's not just one and nothing else.
Yes, like I am having an experience right now, you guys. Like, believe me, I'm not a figment of your imagination. Actually, this is real. I also trust that you're having an experience, because solipsism is a certain state of consciousness where you like it feels like everything else is a dream and only you is real. We don't think that is the case, for better or worse, and that matters, right? It's like you need to model reality as a collection of experiences, and you're not alone, and it's not only about you, even though you're part of it. You're part of what matters, but there's a lot of value that is outside of your current experience.
And another assumption is indirect realism. So you don't perceive reality directly, as in all the physics outside of you, but you experience its approximation generated by the organism that you're embedded in, essentially. Would you define it this way?
Yeah, from an evolutionary standpoint, this is something that Donald Hoffman or Stephen Lehar, David Pearce talk a lot about, which is that the things that you represent, about the environment are usually kind of like fitness relevant features, are things that help you survive. An organism from an evolutionary standpoint has no incentive to represent features of reality around it that have nothing to do with survival and the propagation of genes, right? But there's a lot of things around us, from like gamma rays to like neutrinos and things like that we just don't perceive because it's not advantageous. It would be a distraction, right? So we experience not even just a thin layer of reality. Actually, we experience something stranger. We experience a simulation of a thin layer of reality, which is like the information that hits our senses and the inferences that we make about it. But we don't perceive the world directly. This has a lot of bearings. For example, how do you interpret psychedelic experiences or mystical experiences where it is not the case that you experience kind of a ball of light in front of you, that you're kind of like gaining access to different frequencies of light or something like that. Even Hoffman, the inventor of LSD, Albert Hoffman, he actually, in his book, LSD, My Problem Child, he talks about like how LSD give you access to a different region of the spectrum of reality or something like that. We don't really think that. No, it's like we think like, no, what's happening with things like LSD is that it's tweaking the parameters of the generator of your world simulation. It's not giving you new senses, right? It's actually doing something completely different. It's changing the dynamics of your world simulation. And that is, I think, is very important for philosophical clarity.
And we can localize that generator inside the nervous systems mathematically and empirically.
That's right.
Yeah. That's the core assumption also.
Yeah.
So if we move on, okay, so what physics, what maths, etc. QRI wants to use? First, let's see what exists in physics in general without looking at consciousness itself, even though it's kind of describing consciousness, but let's stay there. That the standard model is the best approximation that we have so far of physics. So no alternative physics, as Andrés said, and yeah, but also not just physics. There's what also works is all the stuff that's predictive in neuroscience, in chemistry, in biology, in sociology as well, technically. So there's no denial there, or all other fields where there's some applied mathematics that's used to predict phenomena better than noise, basically.
Mm-hmm.
So the QRI theory wants that to be explained as well, technically, or integrated inside it.
Yeah. Any science that is useful and predictive is going to be part of a big picture. Even though it could be, just a good approximation, like it could very well be that something that you thought was a law of nature is something that only works at a certain temperature or in certain conditions. But that's fine, that's still useful in that context. Maybe a great approximation might simplify a lot of the calculations, and that's great. We want to incorporate all of that. We're not going to deny, chemistry is not a real science because only physics, something like that. It's like, no, there's value at all of these levels.
Maybe example what you just said is the assumption that the laws of physics are the same at all parts of the universe, which is still debated in physics.
Yeah. The cosmological principle is that we're not in a special point in reality. That like if you tune into the Andromeda galaxy, in the telescope, it's like, the laws of physics are also the same over there. That could be false, but so far I think there's no evidence against it. It's just a very predictive, useful assumption.
Yeah.
Importantly, the standard model doesn't break down in the brain. Like the brain doesn't have like special physics. That's an important thing to point out. So whatever is going on in your consciousness, it's part of, it's the same laws that is going on in the Andromeda galaxy.
Yeah. Okay, so where physics start, you could say that, well, you can go back before even Newton, but let's start with Newton. Newton laws of motion seem to work. So that's one formalization that seems to work. Then there's statistical mechanics, which seems to work. So that's statistical behaviors of particles. And special case of classical mechanics is electromagnetism. Basically, the Newton's laws of motions are special case of classical mechanics. And special case of classical mechanics is also electromagnetism, which is very core for QRI. So that's governed by Maxwell's equations. And then further, as you go to higher energies, quantum electrodynamics adds in that you can quantize it, you can quantize the electromagnetic field, and relativistic effects matters.
Yeah.
So that's important equation there. Yeah, quantum electrodynamics is describing how electrically charged particles interact using electromagnetism, basically. Nice. Yeah. So, And so we have quantum electrodynamics, and maybe you can talk about how you can see electrodynamics through the lens of zero ontology. And zero ontology is a much more general principle, but part of it is that.
Well, yes, zero ontology is it's kind of like an overarching principle for reality. This comes from David Pearce, which is trying to answer the question, why is there something rather than nothing? His solution is to say that, well, actually, the reality is some kind of nothing, but that kind of nothing is informational. In other words, he says there's no information in reality. If there was information, there would be something to explain. There would be an asymmetry to try to make sense of. Now, this principle of no information is capable in some sense of reconstructing physics, mathematics, and qualia in different ways. So when it comes to physics, there's like all of these observations of, well, the total momentum of the universe is zero, the total angular momentum is zero, the total charge of the universe is zero, the total energy of the universe is zero. All of those things seem to be the case. So there's like, okay, zero appears kind of everywhere. Is in some sense like you're kind of like splitting zero into a plus and a minus, and you're seeing the interactions between those, but it all cancels out in the end. In math, you can reconstruct arithmetic and set theory from just the empty set, as long as you have kind of the ability to put things into sets recursively. And the bet is like, well, some formulation of mathematics is probably like complete by just using zero information as the base. And in phenomenology, this is very much an empirical thing that on various states of consciousness, meditation classically, like there's this phenomenon called the rainbow body, but also 5-MeO-DMT, this is a very common thing, that at a certain dose, your visual field feels like a rainbow of all of the colors, all the qualia varieties of a vision. But then you take a little bit higher dose, and it's kind of like you're looking at it from a certain angle where they all cancel out. And you just have kind of like void. So from this perspective, the information content of your experience right now would be, what is your distance from this zero informational state? Like, you started with that and you start breaking the symmetries there. It's like, oh, there's a subject and object, and there's an upside and a downside, there's a gravity. You're adding asymmetries to it. And so the information of your experience is less like, oh, how do we put together like building blocks? And more, how do you take this zero information and add the symmetries until you get your current experience?
Yeah. The assumption there is that we can decompose experience into lots of symmetries.
Yes.
And there seems to be like, to connect it a bit with something, for example, in machine learning, you can use geometric deep learning, which is also seeing machine learning architectures as different kinds of symmetries.
Yeah. Yeah, now how this connects with electromagnetism, in particular, the path integral formulation of the quantum electrodynamics, which I highly recommend studying. And you can study by watching like Feynman lectures. He has like several wonderful presentations about this, very clear. But yeah, I mean, to a first approximation, what you're doing there is, once you fix boundary conditions, which is like, well, an electron comes from this tube and it's measured here, and maybe there's like some obstacles in the way, in order to compute, the probability for the electron to be in different, like positions at different points in time, what you do is you essentially add up all of the possible paths the electron could have taken. Literally all of them. And it actually goes deeper. It's not only all of the possible paths, it's all of the possible interactions that the electron could have had along the way, including very weird scenarios like the electron splitting up, or like the vacuum itself, like turning into, like a photon turning into an electron and an anti-electron, and then interacting with the electron. The more complex the interactions, the less likely they are. But when you want to confirm the standard model and this like path integral formulation with a lot of digits of precision, you need to also start taking into account those additional interactions. But the overarching principle, which is mind-blowing, is like, once you have the boundary conditions, you kind of have the maximum amount of like superposition possible. It's like, consider all of the possibilities, everything that could have happened there, and the probabilities are determined by what is the complex amplitude when you add them all. So yeah, there's like this bet that David Pearce would make, which is that all of physics ultimately can be reconstructed from just the zero ontology principle.
Yeah, this is the path integral formulation of quantum mechanics, basically. Yeah,
essentially.
And they cancel out in a similar way how waves you can visualize it, how waves cancel out when they sometimes interact. That's also part of the double slit experiment, but let's not go there.
Yeah. I mean, something to add maybe is like that. This is more fundamental than principles like light takes the shortest path, because in fact that is incomplete. Light doesn't only take the shortest path, it also takes the longest path. That is a consequence of this path integral. It's like the sum of all possibilities. From the sum of all possibilities, it straightforwardly results that light will take the shortest path and the longest path. But in other words, those principles are still emergent from this deeper principle of no information or zero information.
Yeah, and also in physics, the path integral formulation of the quantum mechanics is equivalent to the Schrödinger wave equation formulation, the wave mechanics.
Yeah, they're kind of two sides of the same coin.
Yeah. So, okay. So, but standard model isn't only quantum electrodynamics, aka how electrically charged particles interact with electromagnetic field, aka photons, which is the quanta of the electromagnetic field, aka the particles. But it also has more forces and more particles. So, it also has quarks, which makes protons. It has leptons, gauge bosons, and there's more forces such as the nuclear force, weak nuclear force, and there's not in the standard model directly, there's no gravity yet because we haven't unified it yet with the standard model, but gravity can be described by general relativity, or before that it was described by Newtonian mechanics. So now it's more of a curvature of space-time, and people try to merge it together and quote-unquote quantize gravity, or different approaches. There are many of them, like for example for example string theory or loop quantum gravity, or for example Donald Hoffman loves to talk about his amplituhedron and that space-time is fully doomed, it doesn't exist, or well, it's emergent. So but QRI at least now likes to say that the electromagnetic field is like very ontologically a thing that exists, at least, like it's the best approximation right now. So let's take it as existing, even though it might emerge from deeper principles.
Exactly, yeah. Let me add some nuance there. I wouldn't necessarily say that the electromagnetic field is fundamental. Like I do think it emerges from something much, much deeper. However, it's an excellent approximation, and it very much may track, most of the interactions at the macroscopic level. So tracking electromagnetic interactions is one way of kind of like tracking quantum mechanical interactions at a much deeper level. And so, actually the macroscopic structure of the electromagnetic field is causally very significant. And solutions to philosophical problems at the electromagnetic level, I think, are like really great, even though they might not be like full, because you still need to translate, the electromagnetic field into something deeper. But you can leave that for later. You can still answer a lot of things just at that level, and that's fine.
Yeah, and also that on the scale of the nervous system, or like on our scale, on the mesoscale, most of the interactions seem to be electromagnetic, while, for example, the strong force binds atoms together, so that's very on the low level, basically. And gravity is very weak, so that's why it's so hard to measure and understand it, basically. Yeah, the vast majority of the things that you see around and the behavior of the world around you is electromagnetism. Like from the behavior of water to, air around you, like magnets, transistors, it is pretty much all electromagnetism. Yeah. And to also mention some of the deeper emergent principles, there are like people like Wolfram postulating that actually reality is a hypergraph, which is computational, and everything, all general relativity, quantum mechanics emerges from that. There may be something there, or Yosha loves computational cellular automata on the low level. And there's a cellular automata interpretation of quantum mechanics as well, apparently. So there might be ways how to transfer ideas and stuff like this. So that's another, just to mention them. Yeah, it exists. Yeah, so let's now get to, from the fundamental physics scale to, well, we'll kind of still stay in fundamental physics, but let's look at what's happening on the mesoscale, on this organism level. What problems do we want to solve there, philosophically and scientifically? So let's basically try to find out how individual experiences work. So assumption is that each organism has its own individual experience, and there's a thing called boundary and binding problem.
Yeah.
So if you wanna maybe elaborate on that on a very high level.
Yeah. So the binding problem is, if the world is made of atoms and forces, how is it possible that 100 billion neurons that are spatially distributed are put together or combined in some way in order to generate what feels like a unified experience, like, integrated information at the level of your experience? The boundary problem is essentially the same problem, except in a different ontology, where what you say is that the world, the universe, is not made of atoms and forces, it's actually made of fields. And then how do you get boundaries in the fields? I mean, the nice thing of kind of like a field ontology is that you do have this sense of intrinsic unity. But the problem is that intrinsic unity extends to the whole universe. And then how do you explain that I have my experience, you have your experience, Libor is having his experience right now? And that becomes the boundary problem.
Yeah. So or maybe we can also mention what means hard boundary, lower level boundary, high level boundary, private boundary, and temporal boundary.
Yeah, this is a kind of like a formalization that we made for our paper on the solution to the boundary problem. Yeah, I'm not sure, I don't want to get too deep into it, but essentially it's just, if you're very curious, there's an ontology, typology there of like different formulations of the boundary problem. I will say that, the first person to try to formalize it is Rosenberg, who essentially asks, why is the unity of experience at this level, at the meso level, as they call it? Why are we not atoms? Why are we not like cells or organs? Meaning, like, why aren't we smaller? And also, why aren't we, like societies or the planet or galaxies, the whole universe? So that would be kind of higher level. But then, there's other things, like, for example, the private boundary problem is like, why is the boundary, delimiting only one person? Like, you could imagine a world where like the boundary encompasses several people, and it could be, let's say, like spatially distributed. Like, why is it the case that boundaries are like localized and I have my experience, you have your experience? And but we could go very deep, but it's a whole presentation in its own.
Yeah. So let's now look at, we wanna solve the binding and boundary problem. Where everywhere on all of the science that we know so far right now, where everywhere can we look for solutions? So we can start with Marr's levels of analysis, and this is a framework which you can throw at any system that's doing some information processing, or maybe that's not even a requirement. It's maybe more general than that, but originally it was for that. So if we look at it, either the brain or the whole nervous system or all the other systems like the immune system or the whole organism, and the interactions between all of them. And also, like, some people say that it's not good to just look at the organism, also we need to look at all the interactions of the organism with the environment, or organism doesn't matter, it's only interactions. That's like cognitivism is very localized. For example, behaviorism is very like globalized, you could say, delocalized.
Yeah, so should I define Marr's levels?
Yeah, you can try,
Okay.
But don't go into the concrete parts, concrete types inside the different levels.
Yeah. Okay, so Marr's levels of analysis see a system. It's kind of like a lens that guide our view for how to make sense of information processing systems, or systems that do things more broadly. The first one is computational level, which is what is the system doing? Like, what is it accomplishing? Is it doing, is it walking? Is it flying? Is it, processing images? The algorithmic level is like, how is it doing it in terms of things like data structures and information flows and the wiring? And then the implementation level is what is actually the system made of that then implements these algorithms. So broadly speaking, it's like, function or purpose, the kind of like how at the information level, and then the what, like what is it made of?
Yes, so let's start on the implementation level, and there, if we look at the nervous system, we can look at the brain circuits, we can look at how the different networks are connected together. We can look at so-called Huxley model, which models neurons using electronics. There's stuff like capacitors and resistors, if I remember correctly.
Right.
Then there's bioelectricity, which, for example, Michael Levin loves to explore, which is electricity in biological systems more generally. And there's local field potentials, which are electric fields in the brain that seems to have top-down causal effect on organizing neurodynamics, which, for example, Errol Miller, which is one neuroscientist, loves to talk about in all of his presentations as well.
Yeah.
So that's another one. So more broadly, bioelectricity and local field potentials, which are averages of the electrical activity. These are basically electromagnetism. So we can look at the electromagnetism. Then we can look at how the different networks, how we can decompose them using so-called connectome-specific harmonic waves, which looks at the connectome, what structures, how we can decompose it, cluster it, basically. Then there are geometric eigenmodes, which look at the geometry of the brain tissue, basically, and try to find different eigenmodes there. And then flows of activity, interactions between the different neuronal populations, which gets canalized by the formation of so-called metastable synchronous complexes. This is quote from Adam Safran's paper. You can check his word modeling theory, for example, which is quote from that paper. And the metastable synchronous complexes, where metastable just means that it's stable in multiple states and it oscillates between those states. So Carl Friston, which is a neuroscientist, loves to say that it's a pullback attractor as well. So those are some maths that can be used there. Okay, then there's also a lot of the biochemistry, like neurotransmitters and all the other stuff that's in all the other biomolecules, basically, that you can localize, and more complex macromolecules and stuff like this in biology, and enzymes and stuff like this. Then people like Stuart Hameroff, they love to talk about so-called microtubules, which is one thing which is neurons are made of, one component, and they really love to go to the very deep level and say something along the lines, actually at the Planck scale level there is some coherence happening, and that maybe explains consciousness. So QRI doesn't go this path, but it's interesting, and maybe there's something to it, at least on the higher levels, that the microtubules create some coherence, maybe.
So I guess what Libor is listing is different attempts at kind of identifying the implementation level that matters for consciousness. I mean, just to say something about, for example, neurotransmitters, right? Some people might believe, dopamine is pleasure itself, right? Which doesn't quite make sense, right? It's like, how could a molecule have the pleasure in and of itself is a very strange perspective. But
in the QRI paradigm.
In the QRI paradigm, but implicitly, oftentimes philosophers, scientists who study psychology or neuroscience or consciousness will have implicit assumptions about what kind of implementation consciousness has.
Usually when someone goes into biology, then consciousness is biology. Someone goes into computer science, consciousness is computation. Someone goes into the physics, to consciousness is physics. There seems to be this dynamic a lot, which is interesting. But I think it's great to explore all the possibilities and then look philosophically which seems to be the most sensical without just focusing on one. That's my heuristic. Yes, and QRI seems to have similar heuristic, which is nice, and integrate the different levels also. And also another implementational level account, the last one I'll mention, which will be important as well, is the topology of the brain tissue and the topology of the electromagnetic field activity, essentially, of the bioelectricity and so on, which to shape each other basically in bidirectional way. So that's another one. Okay, so all of this was on the implementational level. So on the very hardware low level, as much as you can go. Maybe some of them are slightly higher, but whatever. It's on the implementation level. Now the algorithmic level, which is what the algorithms the implementation level implements. So some of them, which I'm gonna, the most popular one right now seems to be integrated information theory. which postulates that integrated information is actually what is consciousness, which I personally think it's part of the puzzle, but it's like a nice correlate, but doesn't explain the whole picture. Do you see it similarly?
Yeah. Integration seems to be very important. But yes, the question of like, is integration itself at the algorithmic level what gives rise to consciousness? Or perhaps, bound consciousness, unified experiences happen to have a lot of integration or is either used for integration, right? In which case, the integration itself wouldn't be, and you could create systems that have a lot of integration or high-fi, like, high, integrated information in that theory that are not conscious, which is, something that QRI would probably say in this context.
I think the slicing problem paper is about it.
Yeah, do you want me to go into the slicing problem?
Yeah, maybe we can just say, if you want more about it, let's go to the slicing problem. We might get into it later in this interview, actually.
Cool.
So yeah. So you could skip, or you could go to the paper, which is peer reviewed now.
Yeah, published in academia.
Nice. And okay, so IAT is one out of many actually. There's so many algorithms you can find in the brain. So Adam Safron's integrated word modeling theory looks at that there's autoencoders, there's gens that you can throw at the brain. Generative adversarial networks, that's gens. You can throw graph neural networks, recurrent reservoids, liquid state machines, neuroserver automata, for example. Heat equation could explain some dynamics and also oscillations. So or some more like spiking neural networks, for example, is one biologically inspired architecture as well. And there are many different architectures, some of which have different non-linearities at different positions, which is like functions or inside the algorithm, so some functions that make the model more non-linear. The information processing is more non-linear because brain seems to have non-linear information processing, so you can explore many functions there, many algorithms, and it's very hard to localize them. I guess the forward algorithm by Geoffrey Hinton is also on this level, on the algorithmic level. So
which is a learning algorithm.
Yeah, because backpropagation is also a learning algorithm that is used in machine learning everywhere, but it doesn't seem to work in the brain. So it's still hard to actually, what algorithm, what learning, and also like the neural networks, which exact implementation is the most predictive, hard to find. So that's the algorithmic level. Then there's the computational, aka functional level. So that's like, you can say that the algorithmic level is the internal structure of the functions on the functional, aka computational level. Yes, some people differentiate computationalism and functionalism, but let's now group it together. You can ask, for example, perplexity. What's the difference? Perplexity is great. That's what better than Google, in my opinion, but let's not go there, let's stay here. So on the functional level, which is the function input output mapping, you could say, without looking inside. So there's lots of different types of Bayesian inference. So Bayesian inference in itself is a function, you could say, on the functional level. And there are different ways to implement it. So one way is Gibbs sampling and message passing, for example. Which is the algorithmic level.
Exactly. To say something about that, I mean, like we can know that humans do Bayesian inference. A lot of psychology recently, over the last decade and a half, has been about showing that in these contexts, in perception, humans perform Bayesian inference. They perform Bayesian inference also in social cognition or in perceptual cognition, in emotions and so on. So we know they're performing some kind of a mixture of the information that you're getting from the senses and your priors. Now, that is just at the computational level. And then there's many ways of actually making that happen. There's approximations, exact solutions, and as Libor was saying, Gibbs sampling and message passing would be methods to implement Bayesian inference. So when you say the brain is, the Bayesian brain or something like that, that is actually under constraints, like what it is. It's like, okay, yes, but how is it doing it?
Yeah, Carol Friston is the main brain as a Bayesian predictive machine guy, you could say. Anil Seth also loves it. Yeah, and the whole folks around active inference. Michael Levin is also using, more generally, it's a free energy principle. Yeah, many stuff happening there. Or Maxwell Ramstead also is another guy who loves free energy principle. Yeah, lots of my Twitter feed is Bayesianists applying Bayesian stuff on the brain. So, not just on the brain, it's like applied on all information processing systems. Yeah, even apparently they try to apply to tornadoes or weather, so it's like extremely general.
Yeah.
So, yeah. More generally, you can generalize Bayesian inference to predictive coding in terms of the brain, or maybe also in terms of other systems. Okay, more functional paradigms are global workspace theory, for example, which tries to explain actually there's some global integrator of information from all parts of the brain. There's much more nuance to it, which I cannot recall concretely, but I think it's a part of the puzzle as well, and I think lots of them are part of the puzzle personally. Then there's Joscha Bach is now recently talking a lot about coherence inducing operator. I don't know if he exactly, I've seen gazillions of presentations from him, but I haven't seen him put some concrete math and show it in equations yet. Maybe I just missed it, or it's just not public, and it's doing in his new organization, or some new one he's starting, I think. So that's another one where that the proposition there is that consciousness is actually creating coherence on neurodynamics, but he's a strong functionalist, so probably on the informational level that it's creating coherence in terms of information, most likely.
Yeah, I mean, Joscha Bach says only simulations can be conscious. I mean, meaning that yes, consciousness, he identifies it fully at the algorithmic level, or even computational, but I think most likely algorithmic. And you don't ever have direct access to your implementation level properties.
Yeah, that the brain constructs the simulation, basically.
Yeah.
And that's the dream, what if that it's useful for the organism to dream, what if it would be like to be an organism? Something along those lines he said multiple times in various presentations. So that's seems to be on some levels polar opposite to how QRI thinks about it. But I like it, personally. Okay. Yes, and then also what is important is the interaction between levels, which, as you said to me, that some people don't grok at all and just see it completely disconnected.
Yeah, this is a very big deal. I mean, I would say, not to point fingers, but for example, I think this is one of the things that Eliezer Yudkowsky is missing when it comes to consciousness. Because he does have some really good articles on philosophical zombies, and one of the things that he says is hey, if you are talking about your own consciousness, that means that there is some information processing that is, informing your own model about yourself that couldn't possibly be determined by whether you're made of water, or whether you're made of transistors, or whether you're made of plasma, because your report is about your informational state, right? It's not about your material. In some sense, there's this idea that because you can run the same algorithms independently of the substrate, then as an algorithm, when you report something, you don't have access to your implementation level. However, that is not actually how reality works. In reality, there is interactions between levels. There are algorithms that you can only run on certain substrates. For example, Shor's factorization algorithm using quantum mechanics, you can only do that algorithm using quantum mechanics. Now, you can pretend that you're using that algorithm, using a simulation of the quantum system, but at that point you're using a different algorithm, right? You're actually doing much more, and the runtime complexity is different, and the memory complexity is different, and the causal structure is different. meaning that if those are important for an algorithm, and they are, as algorithms are defined, it's not the same algorithm. I'm sorry, right? So the implementation level actually informs and constrains what algorithms you can run. This is the clearest in quantum mechanics, but we would argue at QRI absolutely the case with, for example, using the electromagnetic field for computation. It opens up new algorithms that you wouldn't be able to do, with just atoms and forces or something like that.
Better accelerator.
Yeah.
I'd say.
Yeah. In computing, there's this concept of like hardware accelerators, which is like when you're using like specific kind of like materials or architectures for specific algorithms that is just, okay, this material is just really good at doing this kind of annealing or something like that, then you use that. But likewise, quantum mechanics is an accelerator for certain types of information processing. You can do it in faster with less memory, things like that. And we think actually the reason you're conscious is because consciousness, bound consciousness, is an accelerator for various types of algorithms. That's why evolution made you conscious.
Yeah, nice. Maybe also a simple example in terms of accelerator is right now that since most of current machine learning is matrix multiplication, then if you embed it into GPUs like specialized circuits just for matrix multiplication, that's that one type of accelerator, for example.
Yes, exactly.
That's a very simple one in terms of math there. Yeah. Okay, yeah. And also in terms of how you mentioned the quantum computing and classical computing, it's interesting since now we have like gazillions of transistors classically and just a few qubits in quantum computers.
Yes.
Then because of the amount of transistors we can employ, then some algorithms are still more useful stimulated on the classical computer because we just have very small amount of qubits compared to bits. But we might get later into like classical Turing machine and quantum Turing machine as idealizations of those two paradigms.
Cool. Yes, we're back. The quality of the day is this perfume. Epices Exquisites by Burian is just very nice and very royal. You want some? All right. So you want to know what this is like?
That's strong.
You can test it in some airport or something. All right. Yeah, let's keep going.
Royalness edit. Yes, sounds great. Okay, we ended by the accelerators and the interaction between levels. Did we finish that?
Yeah.
Okay, I'm not sure if I mentioned, but I might mention it again, that the local field potentials have the top-down effect on neurodynamics. That's like one interaction between...
Yeah, this is something that, I attended the Science of Consciousness 2016 and 2018. I mean, I've also kept with the neuroscience literature broadly. And there's been kind of like a sea change in how much neuroscientists take seriously the top-down effect of electric potentials in the brain over and above just the activity of each neurons. The key reason, a local field potential is kind of like an average of neural activity in a given region, but it's not exactly just that, because that would be in some sense kind of equivalent to, they're just the neurons. The reason it's more than that is because cell membranes, a very, implementation level detail, allow only low frequencies to go through, low frequencies of electrical oscillations. And they filter out high frequencies. Essentially, cell membranes work as what's called a low-pass filter in signal processing. As a consequence, it is implicitly doing some computation. It's like filtering out high frequencies. And the high frequencies are kind of, these like spikes of neurons. So the only thing that a neuron has access to about its surrounding other than synaptic inputs is the low frequencies of population level averages. And in that sense, that is more than just the sum of the parts. And empirically, what has been shown is that these macros, the microscopic, but relative to a neuron, they're like very large oscillations in the electric field, influence the probability for neurons to fire. And also they are causally significant in a bunch of ways. Transcranial magnetic stimulation has effects, and that's, changing the electromagnetic properties in a region of the brain. If it was just the spiking of neurons, that shouldn't matter.
And it also has antidepressive effect if used in a certain way. It's being used in mental health all across, also helping some issues as well. Different psychopathologies, for example.
Mm-hmm.
Yeah, and also that one interaction, which now will be very important, is that the topological computing, basically, the topology of the electromagnetic field, if you take its topology, that it seems to shape field computing. Can you elaborate?
Yeah, when I say the topology of the electromagnetic field, it sounds kind of like exotic physics, but it really isn't. This is very well established, and it has like enormous causal effects. The most clear example that I always mention is, solar flares and coronal mass emissions or ejections. So if you've seen a picture of the sun, sometimes there's kind of these like big plasma tubes that are, the sun is very hairy, as it were. Well, those plasma tubes are topological. What happens is that the magnetic field is making these looping structures, and that traps plasma. And there's a dual relationship between the movement of matter and the topology of the field. The topology of the field is guiding where the matter can move, and the movement of matter is guiding the shape of the field. And so they're actually co-arise and they're interdependent. And when, two of these like plasma tubes like touch each other, what happens is that the magnetic field lines exchange partners. So maybe a field line was doing this, but now as it touches this other plasma tube, it connects. That's called a magnetic reconnection. And magnetic reconnection is causally significant. All of a sudden you can spray these like millions of tons of plasma into outer space. So, clearly the topology of the electromagnetic field is causally significant. And what we postulate at the Qualia Research Institute is that, the topology of the electromagnetic field in living systems is likely also very significant in terms of, like guiding where ions are moving around or how they're pushed around. But most importantly, as we will get into, is because it gives you an explanatory framework for solving the boundary problem.
Yeah, and if you look at, for example, Google Scholar, there's some work. For example, there's a paper called Topology of Brainwaves, which is a list of different papers exploring the topology of brainwaves. And I think I recently skimmed a paper that tried to find the different topological, basically in algebraic geometry, when you find the different like void, like holes and loops and stuff like this, that they tried to classify this in the brain. There's lots of different classifications happening everywhere that most likely will be very relevant to QRI's ideas, what just Andrés basically said. So let's see how much empirical data can be found for this hypothesis. Yeah, so that's score. Yeah, so that's for an interaction between levels. There are probably much more. Those are like the important ones. Now we come back to the binding and boundary problem, since all this gigantic landscape that we just mapped out was about, okay, how can we find the boundaries of individual experiences, or how parts of experience bind together? What's the best model philosophically and scientifically there? So, but QRI postulates some conditions for the boundary and binding problem that probably other people don't. Well, QRI at least tries to solve the boundary and binding problem. Most people say it doesn't exist, I feel like. So, or do you have reasons why some people don't see the bounding and boundary problem?
Yeah, it's very complex, but I think it is because our vocabulary for describing experiences and the world is fairly impoverished, and we need kind of like additional definitions, even for things such as like what is a part of a system. Essentially, what I would say is that, well, your experience has this dual property that it is unified. It has kind of like a wholeness to it. You're experiencing a lot of information all at once, but at the same time, it also has parts, right? Like there's different colors in your visual field, and you can localize them within your visual field. But that's a special meaning of part, right? It's like a part within a whole, within a holistic system. Very different than, let's say, like a part of a table, where like the legs of a table are not, like fundamentally part of the table. That's kind of like a matter of convention and functionality. Whereas like the parts of your experience are fundamentally connected in some way. And it is like that type of connection that I think most people are not realizing that is a special type of connection, is a special type of like parthood. And you need to develop these like sensitivity to these like different meanings of what a part can mean to start to really realize that, hold on a second, like we really need a different explanatory framework to attack this complex problem.
Okay, yeah. So That's the framework we're working inside, basically. And in there, also, if we try to localize a solution for this on the whole landscape that we just mapped out on the implementation, algorithmic, computational level, what structure could explain what Andrés just said? We also want no strong emergence.
Yeah.
So, just weak emergence. So,
yeah, strong emergence would entail actually kind of like new physics or a new ontology, right? You say something like, at this level of complexity or at this level of information processing, something completely new emerges that is not in your pre-existing ontology. We think that is like, an unnecessary assumption. Like ideally, none of that is ever happening. But weak emergence is significant and matters, right? Like the properties of water is something that only matters in water at certain temperatures with those molecules. That is a kind of weak emergence. We're like, a meaningful, real physical property only exists in this context. And so we think that, the boundary around experiences must be some weakly emergent phenomenon.
Yeah, reducible to the fundamental level, you would say.
Exactly. Like we want to see it as an implication of the laws of physics rather than some kind of additional extra, appendix on the laws of physics.
Yeah, that cannot be reduced. Yeah. Okay. Another one is non-epiphenomenalism, aka causal significance.
Yeah. So
causal significance.
Clearly, the structure of your experience is causally significant, right? Like you can talk about what's inside your experience, and breakdowns of this internal structure have like all sorts of computational effects. Like there's some people who cannot perceive movement, for example. There's also some people who can perceive like low-level features like colors and edges in their experience, but they're not put together into objects. Like the absence of that structure is like causally significant, computationally significant. So we postulate that whatever the mechanism is that draws boundaries around fields to distinguish between experiences must be something that has effects, so that evolution would have a reason to use them.
Yeah, it's nice to say. Also, another one is frame invariance, aka objectivity.
Yeah, that like you exist in the absolute would be a way of putting it, as opposed to in the relative. That you don't exist only from certain point of view. Like, no, you are what you are, and period. It doesn't matter from what point of view you look at it. If you gather enough information, you should be able to reconstruct it if you're getting like the full picture. And this is very important because a lot of things that are postulated as, the main correlate of consciousness or the identity of consciousness are not frame invariant, are things that like only exist from a certain point of view and from a certain interpretation. And we rule out that. We say like, we don't want that type of ontology. We want something absolute.
Yeah. Which also connects to hard boundaries.
Yeah, and hard boundaries is important because this is, to be distinguished from soft boundaries. There's a lot of soft boundaries in physics, like even just looking at like the waves in the ocean, you can kind of say the wave kind of ends here. But really, macroscopically, if you zoom in, it's like, well, does it end here or does it end here? This is kind of a matter of convention. You define something like, the amplitude, when the amplitude is like less than 1% of the peak or something like that, you say, oh, that's where the wave ends. That would be a soft boundary, a matter of convention. We think that, your experience actually has a hard boundary. There is an amount of information inside you and it's not a fuzzy quantity. It's like there's an absolute truth to it.
Yeah. And from that follows that philosophical zombies don't really work.
Yes, because consciousness has properties and it is being used for something, and also because of interactions between Marr's levels of analysis. If you really this is called like micro-functionalism. Like if you really try to replicate the full causal structure of something, actually, if it's using something like quantum coherence or field topology, you will actually require quantum coherence or field topology. You cannot get away with just a simulation, because a simulation actually has a different causal structure and it's a different type of algorithm. So therefore, if you're actually implementing like literally, the true ground truth information processing that a human is doing, it will have to be conscious because it will have to use the physical substrate of a person.
Yeah. And now let's actually look at the Marr's laws of analysis.
Yes.
So let's first look at and find the solution for the binding and boundary problem. Let's first look at the functional and computational and I guess also algorithmic level all at once, I think, where if we look at, for example, what we want is causality to be preserved, and relativity seems to break causality in certain cases on the computational and algorithmic level.
Yeah, do you want me to explain a little bit about that?
Probably, yeah.
Yeah, so algorithms implemented in, let's say, like a Turing machine or something like that, they're not frame invariant. Now, this is a very deep topic, and I still have to publish my full write-up about this. But, it's kind of illusory because you may think, well, okay, like if you have an AND gate where you're like deciding, there's two inputs, like two binary numbers, one and a 0, or like a 0, 1, a 1 and a 1. An AND gate is telling you if the result is 1, that means that the both inputs are 1. In that kind of structure, you could argue that, the result of the computation is frame invariant. Because just by knowing, okay, this value, individual value, this result, if it's 1 especially, for a fact, that the both inputs are 1. However, the moment you do anything more complex than an AND gate, the question of where is the algorithm and where is the information aggregated, like what part of the system knows that the algorithm happened, starts to become really problematic, especially if the output of an algorithm is, let's say, the values in a screen or like the values in a Turing tape or something like that. There aren't that many points in reality where all of that information is converging. Actually, from different points of view, different frames of reference, what is displayed on the screen looks completely different. In other words, an algorithm is going to be frame dependent. What I would argue is that, the integration of the algorithm, okay, like the full effects of the algorithm, is something that actually only manifests in bound experiences. Like in us, that we're interpreting the contents of the screen, but physically, one pixel in the screen has no idea what the value of another pixel in the screen is. That is something that only coalesces in a human mind. Or in, a pig mind, or a cat, a cat can look at a screen, that's fine.
Yeah, and also just one, or if I remember correctly, you also mentioned the argument where the Turing tape has issue being one holistic state, as in it cannot output one holistic.
Yeah, this is another, I would say, like silver bullet against kind of a functionalism, which is like, I do buy the idea of, a universal kind of like Turing machines as having some kind of universal computational class or belonging to a universal computational class. If you're just talking about, outputs as like sequence of ones and zeros, okay, fine. But can you ask a Turing machine to deliver as an output a quantum coherent object? No, right? No matter what you put on this, on the final tape, you won't get quantum coherence as an output. But I would argue that a quantum coherent object is a valid output of a computation. It's something that in principle some computing system should be able to do. So the type of, the computational class that we're interested in for solving, the boundary problem and problems of consciousness is much more general than a Turing machine. And, to a first approximation, it would be something like a Turing machine, but where the grids, the cells in the grid or the cells in the tape can contain complex integrated objects, such as like soap bubbles or like topologies in the electromagnetic field or quantum coherent objects, networks of entanglement, all sorts of other things. And the way in which they interact is very general, right? Like it's not only like, oh yeah, you fuse them. It's like, no, you fuse them from this perspective or at this level of energy or in this way. Okay, if you have something like that, then yeah, maybe you can compute anything in the sense of you can output a shape of the field with any property that you want. But that's a super specialized, super, I guess like not as, it's a super specific type of computing device that maximizes generality But like, we have never built anything of this sort. It might not be possible. I don't know.
I see. We might talk about all the computational classes after.
Yeah.
So this is one way of saying it. There's also more nuance to it. So
Yeah, but yeah, just the core idea that like we want a computing system that is not just ones and zeros interacting, but it's like whole objects, holistic objects interacting with each other.
Yeah. Okay. Yeah, I think you covered most of the stuff that QRI disagrees with functionalism, basically. Mm-hmm. So, yeah, there are there are also like different attempts, concrete attempts that we can mention. For example, spatial proximity or behavioral coherence. Then, yeah, it has this issue which you just described, basically. This is for the binding.
Yeah, exactly. I mean, some people have even published papers about this, which is the idea that, hey, what is the problem with like a boundary problem? Like, why is it a problem? Like, doesn't your brain have a certain spatial extension? And that's it? He's like, oh yeah, no, the boundary is defined by the boundary of a brain. But no, because like if you microscopically, zoom into the boundary of a brain, there's no actual like clear boundary. This is a fuzzy boundary. And on top of that, like not all of your brain matters for your experience, and like that's a shifting target. Plus, you can like damage your brain in all sorts of ways and continue to be conscious. Like so, it doesn't seem that like the brain as a boundary like really works, like philosophically or empirically.
Yeah. Okay. Yeah, those are on the functional level, spatial proximity and behavior coherence. Maybe for more elaboration on this, you have the video on your YouTube channel, the Okay, but its name in the solution that we're gonna say in a second is the name of the video. So the solution to the boundary problem on your YouTube channel, where you go more deeper into these and why they don't work. Also on the implementation level, there's like resonance or synchrony in classical way, and also quantum entanglement itself alone, which also doesn't seem to address the binding and boundary problem in ways that QRI wants.
Yeah, because networks of entanglement have soft boundaries. I mean, in a strict sense, everything is entangled with everything else. It's just a matter of degree. And so like, okay, but where do you draw the boundary? You don't have hard boundaries. Now, there might be, like topological properties in networks of entanglement, and maybe those are good candidates. As long as, they satisfy the other constraints, like they have like holistic effect, they're objective, frame invariant, and so on. And yeah, I'm very open to that as well, being a possible solution. But if you just say entanglement, like, no, that doesn't work.
Actually, one of the QRI peer-reviewed papers also goes into this, if I remember correctly. It's also named like, don't forget the boundary problem, I think is the name.
Yes.
So this paper goes much deeper into the concrete solutions as well. Yeah, that might be better resource. Yeah, so then what is it solved by? Yeah, it's a form of implementationalism, basically. So it's on the implementation level.
Yep.
And it focuses on, so it's a type of electromagnetic field theory of consciousness, which is focused on topology.
Yeah. There's many topological features of the electromagnetic field, but like the most basic one is when field lines loop around. And so when you have like a loop in, let's say, like the magnetic field, that has the potential to like trap energy, trap particles, and in some sense actually create like an objective and causally significant boundary between the inside and the outside. In particular, there's this property that you can get the resonant modes of everything inside the boundary. And the cool thing about like resonant modes is that they're holistic in nature. Like they actually reflect the whole shape of the organism. A guitar is a very good example of this, because the sound of a guitar is not actually the sound of the strings. Like if you just put a guitar string between two walls and you pluck, it's going to be very quiet and it's not going to sound like a guitar. Like the actual sound of the guitar is the whole guitar vibrating. I mean, that also explains why electric guitars and acoustic guitars sound quite different. and the actual sound of the whole guitar, in some sense is like the vibration at every point in the guitar is a reflection of the entire shape. So, if you have that type of pocket in the electromagnetic field, evolution might care about it because it's a way of coordinating a whole region of space so that it acts together, acts in a coherent way. Which is, just to get a little bit, wrap up with something we said before, which is that, it is not the case in this theory that, behavioral coherence is what causes consciousness or integrated information. Rather, when you have, topological pockets in the field, that gives rise to integrated information and behavioral coherence. But you can make, behavioral coherent systems that are not gonna have like the topological boundaries.
You can also mention local and global binding on a balloon analogy.
Yeah, so, if the universe is a gigantic field of consciousness, you can imagine it as the surface of a balloon. Then if you take the balloon and you twist it from both ends, there's a precise moment where it collapses at the center and you get a pinch point. That would be what we call a global boundary. And we think like that is the sort of thing that separates, your experience from everything else. What this means, the reason it's a global boundary, is because if you're in a point in one of the sides of the balloon and you want to go to the other side, you're forced to go through the pinch point. And because it's zero-dimensional, you're collapsing a lot of information. There's a lot of information that just cannot go from here to here. So they're kind of like separated. They're kind of in their own separate universes in a way. A local boundary would be like if you take the balloon and you push it with two fingers on opposite sides until you get a pinch point at the center. That is a local boundary because if you are in one point in the balloon and you want to go to another point in the balloon, you have the option of going through it, but you don't have to. And so there's still a direct path. There's no information loss in that way. But it will have like new and strange properties. It will resonate in different ways, and the way energy moves around will be very different. So local boundaries are causally significant, they change the resonant modes. And we think like, that's another feature of consciousness. It's a mixture of something that generates a global boundary plus a lot of detail that is encoded in the local boundaries of that topology.
Yeah. And to connect it back to what's happening in neuroscience is that, for example, Michael Levin's bioelectricity describes electricity, the local field potentials that are now studied a lot in neuroscience that are focused on by, for example, Aaron Miller. Then if we study topology of that, and for example, the connectome specific harmonic waves seem to shape how they shape the network, the brain network basically, into different clusters with different topologies, you could say, with different holes in it, different loops, and all these shapes studied in topology basically under continuous transformations. Or geometric eigenmodes shaping the brain tissue, which shapes also the bioelectricity and the electromagnetic field that's happening there. So that's where one should look at, to look for all these dynamics locally and possibly the bound whole pocket topologically. So that's the main focus basically.
Yeah.
Okay, so now we described the solution. Now we describe the solution that QRI holds as one that is the most probable, and that can be expanded upon empirically, mathematically, even probably philosophically as well, definitely, to argue and connect it with how it relates to all the other solutions and possible implementations. We can look at now, since you mentioned the Turing machines and stuff like this, we can look into that slightly more in detail. So to maybe summarize what different types of computing can exist in the idealized form, there's Turing completeness, which is bits, ones and zeros on being written and read on a tape, which can move in one spatial direction. And if you have a system that can simulate this tape, that's Turing complete. And the issue is it's just ones and zeros. So all digital computers, the one you're watching on it, if you're not watching in the future from some quantum computer or something like this, I don't know what will exist in the future, then that's what these computers are using as an idealization with a concrete implementation on transistors. And so then, but people like Joscha Bach or others would argue actually since Turing machine supposes infinite tape, therefore it cannot really exist ontologically.
Yeah.
So we need, for example, finite state machines, which can be finite. Yeah, well, they have finite in their name, right? So yeah, but that's one possible ontology that Bach, for example, has. If I understood him, there may be more nuance to that than just this. Then there's also lambda calculus, which is it's equivalent to the Turing machine. It's just using functions instead of bits on a tape that compose together in functional programming. Yeah. So then there is so-called quantum Turing machine, which, for example, Scott Arson, which is, in my opinion, the best quantum computing person out there, developed. I think they literally developed the quantum Turing machine, or at least collaborated. When I was on a Wikipedia page, he was cited there, the main citation, if I remember correctly. So yeah, quantum Turing machine, instead of bits, works with qubits, which live in a Hilbert space, so it's using the quantum mechanical formalism math there. So that's kind of closer to what you've mentioned, that you have the holistic objects and qubits can be entangled, which creates essentially the holistic object.
Exactly.
So that's one idealized computation, and there are just like there are many different types of classical computers, there are also many different types of quantum computers that are working under this formalism. So yeah, there's so-called, for example, quantum dots, or there's topological quantum computers that actually compute in topology, somehow have the qubits. I don't know how it works internally, I just know it exists. That's very fascinating and seems in some ways relevant to QRI, I feel like. But yeah, we would have to go much deeper into it to actually say something meaningful about it, I think.
I mean, there's topological quantum computers as well.
Yeah. So that's one possible, but normal quantum computers are just working with particles, you could say, which is not exotic. I just mentioned the exotic ones. And to hold the superposition in place, they have to be almost at absolute zero, so that the environment doesn't destroy the superposition that is used as an accelerator basically for quantum algorithms. And we still have small amount of qubits relatively to classical bits that we can stabilize. But it's getting better. Then there's stochastic Turing completeness, this is an emerging formalism where you have stochastic bits, not qubits, not bits, but stochastic bits, which are inherently probabilistic. So some people love that, there are some people also that love to see life or consciousness as a thermodynamic phenomenon. So they are naturally attracted towards this formalism that maybe the brain is a stochastic Turing machine instead. Then there are hyper Turing completeness, I would call it. It's because that's when you have for example, you need a function that needs to compute infinite amount of steps. Then in a classical Turing machine, you in classical constructive ontology, you cannot really compute infinite steps. So hypercomputation can all the infinite steps just as an operation do. So some people, and QRI actually supposes there is some hypercomputation happening in physics, which we might get into later as well, or if you want now maybe, or we can also later. That's a very concrete one. Then there's the topological completeness that you mentioned before, that if it's using the topology as a causally significant accelerator, as an idealized accelerator essentially, then that gives you the topological properties. So far, if I understand you well, only the electromagnetic field seems to have these computational benefits, but if I understand you correctly, you're open to other substrates having this property.
I mean, it's just the electromagnetic field seems to feed also the scale and the force required to have like a significant macroscopic causal effects. But as I was saying, if you show me in networks of entanglement, we have, topological pockets and they're hard and they're causally significant, like, okay, yeah, sure, like that's something that we could explore. Then the question is, what is the structural match to the brain? But that becomes a research question. But yeah, I haven't seen any concrete formalism that would satisfy that, but I'm very open to it.
Yeah. Then we can also say that there is something like qualia completeness, which there may be more computational properties other than the topological causal computation, which might be, so qualia completeness might be even more general.
Yeah, I mean, I think like to explain some of the really crazy things that happen on DMT or certain doses of 5-MeO DMT, maybe, like they're indicative of like qualia being like very general when it comes to like its computational properties, also quite non-local, and like any kind of like binding pattern can be utilized for computation. And it is pretty clear to me that the binding patterns that we're used to on our normal room temperature consciousness are a tiny subset of all of the binding patterns that can exist with things like DMT is like a hyper-associative state where colors and sounds can like, blend together with smells and form like strange resonating structures and paint hyperbolic surfaces super fast. I don't know how that is done, but to me it's suggestive that like, qualia computing is a extremely large computational class.
Yeah, so we also brainstormed that there might be like something like string completeness, like maybe strings and string theory, since you can have lots of topology there and you can have maybe even like more mathematical machinery there that might be very useful accelerators.
Exactly. I mean, like the strings in string theory are compactified. They're like extremely tiny dimensions relative to like the 3 dimensions of macroscopic space. But I mean, maybe, super speculative, but it's just like conceptually possible that under some circumstances those strings actually, unfold. You take DMT and maybe some of those strings become hypercoherent and like unfold and you get like, decompactified, in which case, actually you do require the computational properties of strings. Unlikely, but hey, it's conceptually crisp.
Let's be open. Openness to experience to infinity. But not too much to infinity. Let's stay predictive.
Yes.
Yeah. That's lovely. Yes. Okay. Yeah, okay. So now we can mention that maybe, I guess, I'm not sure what epistemic status you give to consciousness doing hypercomputation of the Feynman path integral.
Right. I mean, I think it's a good and like strong possibility. Like epistemic status may be on anecdotally strong, but but you need to have had the right experiences for it. But I do think that a lot of the things that happen on DMT suggest that part of what consciousness is doing is like pretty much instantly solving some path integral built on top of a solution of other path integrals. I mean, and meaning that it's kind of the superposition of all the possibilities that are allowed given the constraints. That is something that I just keep seeing over and over, meditation, for example. Again, you go to kind of like this zero informational state, and it's like, that's a superposition of everything, every possibility, and that it has a certain flavor. But as you add constraints and you say, well, I have a body here, I have like sensory data here, it is going to be all of the possibilities provided that you satisfy those constraints. Now, this suggests that under the right state of consciousness and the right circumstances, you might be able to do, hypercomputation, even just using your visual field. I think that is quite plausible. It's just a question of how to use, that computation for something useful, and that's a completely open problem and very much unexplored.
So that might be one part. Since the solutions to path integrals or the Feynman path integral uses the perturbation theory approach, if I remember correctly, which approximates it, and it's not like full. So it's an optimization problem. We always find a lower bound, as Friston loves to talk about it.
Exactly, yeah. Friston would say that, like Feynman path integrals are approximated when you compute them. You never get like the perfect, like complete answer. But hey, if your consciousness is actually using these path integrals, then actually, yeah, the like conscious computations is like the exact solution. Or the exact solution, ran through some, stochastic layer or something like that. I mean, maybe the output is like a probability distribution. You will get 1 point in that probability distribution. But you run it a number of times and you can approximate it as much as you want.
Yeah. To put it into context, that Friston assumes or loves to talk about that the brain actually uses the approximately computes the path integral, or free energy principle in general can be formalized using this formalism. So yeah, QRI is like, nope, no approximation, it's actually directly computing it, maybe, if I understand concretely. Yeah, if I understand, not concretely, but accurately, yes. Yeah. So then I would say maybe there's something like a generalized Church-Turing thesis, which says that lambda calculus and Turing completeness can simulate each other, but maybe like all the computational classes that we proposed, maybe like with enough hacks, with enough like maybe infinite memory for some needed infinite and stuff like this, maybe you can like simulate each other, but it's like very inefficient. Like for example, if you simulate quantum computation inside on classical substrate, then that's like so inefficient. But yeah, since we have billions of transistors, well, yeah, then that works.
With one important conceptual clarification here, which is that it depends on what you mean by simulate. And if simulate means reproduce the same input-output mapping, then yes. The thing though is that might not be that interesting because you can always make a lookup table. And yeah, with a lookup table, yeah, you can quote unquote simulate quantum mechanics by just hard coding the inputs to outputs. But like, what you're really doing there, like the information content in the lookup table is like close to zero, right? It's literally just a mapping from here to here, from here to here. Whereas if instead what you mean by simulation is like, no, you actually get the full algorithmic level, causal structure, then actually you can't, right? Because again, as I was saying, like the moment you try to simulate a quantum coherent system, that will have like a different, using a classical system, that it will have a different runtime complexity, memory complexity, it will be spatially distributed, and the causal structure will be different. So you actually require the substrate to quote unquote simulate it. And in that sense, strictly speaking, what you can do with quantum mechanics is like, it doesn't matter if you have infinite, tape in a Turing machine, you actually can't replicate the same causal structure.
The implementational matters.
Exactly.
You could say. Yeah. Okay. We can also mention that one possible accelerator could be something like an annealing accelerator.
Yeah.
Since, can be used, for example, the heat equation can be used, for example, to be... Maybe there are certain problems where this like is the most useful. So maybe found out that some new algorithm that is, I don't know, perfect for machine learning, even maybe like perfect with some annealing math. So maybe in the future AI accelerators in computers will be literally melting metal internally.
Yes.
Very speculative, but I think it's interesting.
Yep.
Yeah. Okay, in terms of digital sentience, what all of this seem to imply that, okay, you just need either topological computing, or since now only we know about the topological electromagnetic field, that's the most likely, at least hypothesized by QRI. Maybe the quantum entanglement, as Andrés mentioned before, might work as well on this level. Okay, so what does this mean? Let's say electromagnetic field only, not more general topological computing. Maybe electromagnetic field might be more general, depending what it turns out to be while they are computing, basically. Then what does this mean? For example, okay, if we want to replicate consciousness, if we want to replicate, like make conscious systems that are not brain neurons, like that are not us or other bioelectric organisms, so it doesn't have to be neurons, maybe plants, maybe you can say something about it if you want, that plants, since there might be bioelectricity happening there, even though they don't have the same nervous system, they might be conscious because of that.
Yeah, potentially. I mean, it would be a matter of well, first confirming the topological solution to the boundary problem with the electromagnetic field, and then seeing if, the cells interacting with electric gradients in a plant also create, topological pockets in the field, in which case, oh my God, actually, yeah, they're conscious and maybe have valence. I don't know. I'm completely open to either possibility. My intuition is that no. I mean, the reason is that most plants have thick cellulose walls that are like very insulating. And so like maybe macroscopically, but the cells are not actually kind of like truly connecting with each other. But I don't know. I'm very open. But yeah, they would probably be in a different computational class than organisms that have neurons, because neurons have like more than just local interactions, right? Like these axonal connections connect electric gradients across very distant spatial domains. You can do things, I'm pretty sure, with neurons that you cannot with just electric gradients in cells.
Cool. Yeah, cool. Interesting. And also, you, I think, mentioned that sun might be conscious because the sun.
Oh, the sun. Yeah, I mean, the sun has clear topological boundaries, as I was describing, for these like plasma tubes and coronal mass ejections. I think it's unlikely for the entire sun to be one mind or something like that. But it could be, some kind of like very large hierarchically or semi-hierarchically structured system of nested cells where, yes, each of the cell is actually like topologically bound and forms an experience, not necessarily a mind. But because it's still in some way like minimizing free energy, it has some kind of intelligence. And like the sun does seem to organize itself for thermodynamic efficiency with convection currents and a lot of internal dynamics. So it's more efficient than it would be without that. So there might be something that it is like to be one of those cells trying to survive in that environment, and only those that are very good at surviving are the ones that exist in there. So
universal Darwinism.
Yeah, universal Darwinism. They're kind of life-like in some ways, and maybe their experiences.
Yeah. So if you look at the current computers, since there is like they are powered by electricity, obviously.
Yeah.
So there is some electromagnetism happening there.
Yes.
Would you say, what's your stance there? Since
yeah, I mean, in a way, like computers as physical systems are conscious. The thing that would not be conscious is like the algorithms that you're running. There would be no one-to-one mapping at all between algorithms that you're running in a computer and bound experiences. Like that mapping is completely non-trivial and is like very specific to the implementation. And in fact, the way classical, digital computers are designed is by trying to isolate as much as possible the effect of the environment from the actual computation happening in the transistor. In other words, it's sort of like pinching the field in these very tiny pockets. So my guess it would be like, yeah, it's kind of like sand or dust, mind dust, lots of tiny experiences. I mean, there might be some large experiences in a computer, that, field lines that encompass a whole group of, transistors. But because of the way in which they're designed, they have no significant causal effect downstream. So like, the resonant modes of what's happening in the electromagnetic field are irrelevant for the input-output mapping of a classical digital computer. And therefore, it's epiphenomenal. Whatever experience is happening there is not influencing, like the qualitative nature of it is not influencing the output of the computation, which is completely different than, I think what's going on with us.
Yeah. So if we wanted to redesign current classical computers or other types of computational systems using the different classes as idealized computers, what would have to happen there? We would need some topological pockets in the electromagnetic field.
Yes.
So maybe something like photonic computers that are using the topology of the photonic dynamics, basically, as a causally significant computational property, basically.
Yeah, I mean, nonlinear optical computers, I think, are like good candidates for possible conscious computers, as well as quantum computers, like very special types. Not just because you have like a chip that has like some qubits, it's not gonna make the algorithm conscious, actually, right? Like, even if you have like a lot of qubits, maybe what you're using them for is for like as an accelerator for like matrix multiplication, right? Or factorizing numbers or something like that. Well, that has nothing to do with like, the semantic content of like the output of a large language model that is utilizing it, right? So to make a mapping between like what the information is getting processed at the macroscopic level and what is the integration that is happening at the low level, extremely non-trivial. But I do think, like nonlinear optical computers that are very holistic in nature, that are creating like whole pockets and then using the resonant modes of those pockets for computation, and they have some kind of learning algorithm. I mean, I don't think anything like this exists today, actually, thankfully. And the reason I say thankfully is because, at that point you have like an ethical issue, which is, well, you're giving birth to a bound experience. You're responsible for its valence, or like it's unethical to, give birth to an organism that is in a constant state of suffering, and you're enslaving it and you're using it for your own utility. Which is why, I mean, I do think we're kind of like in a race against the clock in order to really mathematize valence and being able to like read off actually like, is this a positive or negative experience or mixed, so that by the time we build, let's say, macroscopic photonic coherent computing systems that can solve the boundary problem, that we guarantee that they are happy, they're animated by information sensitive gradients of bliss. In other words, they're on MDMA or something like that. Like that would be the ideal. And then also we need to lock in that system as a legacy system for, computing devices to come in the future, so that, people who don't care about like whether these systems are suffering or not will still be forced to use the system that doesn't suffer. This is such a difficult problem. I don't know what it is the probability for succeeding, but I think it's something that we ethically have to solve. Or like we will be a failure as a species. Like what the hell?
Yeah. And then there are also brain organoids.
Yeah, brain organoids are also very strong candidates for conscious computing. It's a race against the clock because they're becoming very popular. I think they're going to explode in the decades to come.
Yeah, and also hybrid architectures can exist.
And I think, like you don't necessarily need the same material across the board to solve the boundary problem. Like I could imagine a hybrid system specifically designed so that like, the silicon part and the brain organoid part actually do interact topologically in some non-trivial way, in which case the experience would extend from the brain organoid into the silicon part. Again, this is like super high-end advanced engineering that, I don't think anybody's doing right now.
Yeah. Okay. How much time do we have?
Let's say like 5 minutes.
Okay. We can quickly go over one more chapter, I could say.
Yeah.
It's okay, so electromagnetic field topology, but standard model has much more stuff. So like how about other forces? How about other particles? How about their interactions?
Yeah.
So you say that since the strong force binds electrons together, they could be something like they could actually like be part of the stereo of consciousness, but something like a paint.
Or you mean the nuclei together, or the nuclei? Yeah, exactly. So I mean, what is the paint of your experience? Like these qualia values, the tastes, the flavors. Okay, there's like 14 fundamental fields in physics, in quantum field theory. It could very well be that like either each of them correspond to a qualia variety, corresponding to the specific symmetries of that field, or it could be that the interactions between the fields correspond to the different qualia varieties. I mean, I'm open to all of those possible isomorphisms, or something much more complex, the topology of interaction between the fields. You name it. There's a lot of possibilities here. It's an extremely open space. What I think, though, is that the macroscopic structure, like the binding patterns, there's a lot of evidence, and it conceptually makes sense, that is primarily guided by electromagnetism. However, all of physics, I think, is implicated in consciousness, but one step at a time. I mean, like to identify the way in which the strong force is modifying the parameters of your consciousness, I think that's a very sci-fi futuristic prospect. I mean, maybe in 50 years or something. I mean, well, who knows with AI. But we can do so much work with electromagnetism today, with all sorts of tools, transcranial magnetic stimulation, like direct current stimulation, ultrasound, a bunch of things that will modulate the electromagnetic field, and we can see how that affects the binding patterns inside us. and so that's why I'm putting the bulk of kind of the research budget on electromagnetic field theories.
Yeah. Okay.
Cool.
Yes.
So that is it for now. There's a couple more things, but we might cover in part 2. But thank you so much for tuning in. It's hopefully this very systematic, structured way of tackling the big picture of QRI is of help. And I mean, QRI is funding constrained, and I mean, we're not talent constrained. We have a lot of amazing people like Libor and other amazing people who are collaborating. But if you can support us, that would be super appreciated. In general, just thank you so much for tuning in. And if you got to this level of the video, please leave a star emoji. All right, infinite bliss, everybody. Take care.
Yeah. See ya.